So we'll just complete another two problems of this conversion from one set of coordinates to other set of coordinates in a multiple integral. So it is simple dx dy dz will be Jacobian times whatever the coordinates are, dr d theta d phi. So let us do this problem. And now this is not a yeah. Now this is not the second question is not a, it is just a transformation. It is not a calculation. Just a minute. This question to transform this integral by this simple substitution. Now, like yesterday, now x plus y is equal to u and y is equal to uv. So what will be x? Y is in terms of uv. X should be a function also of uv. So this implies x is equal to u minus y, which is u minus uv, and y is uv. Now limits of integral. So this is on y. Y varies from 0 to a minus x. Y varies from 0 to a minus x, and x varies from 0 to a. So now what will be the limits on u and v? That we need to check. So this is this line, y is equal to a minus x, means x plus y is equal to a. So in the uv, in the plane here, this is the r region r, x, y. Now a, b. Now this is So x where y varies from 0 to a minus x and x varies from 0 to a. So this is this region in our xy plane. Now, if we want to do this in UV plane, so we need to write the limits. So let us think of writing u and uh, v in terms of x and y. So u is x plus y, no problem. U is x plus y. What will be v? V will be y upon u, which is y upon x plus y. Okay. Now let us apply the integral. First, let us find out the Jacobian. The Jacobian J is dou x comma y by dou u comma v. So let us see what it is. So this will be dou derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, derivative of y with respect to v. All partial derivatives. So this is determinant of first differentiate u, differentiate x with respect to u, we'll get 1 minus v, and differentiate v, x with respect to v, we'll get minus u. Differentiate y with respect to u, we'll get v, and differentiate y with respect to v, we'll get u. So Jacobian is 1 minus v times u minus of v into minus u. So 1 minus uv plus uv, not 1 minus uv, u minus uv plus uv, which is u. So this is the Jacobian. Now, yeah, let us see the limits. X, y, u is equal to x plus y, and v is equal to y by x plus y. This will be the so of course these are not constants. It is a boundary is a straight line. So y varies from 0 to a minus x. This strip has to transform. So the solution now, like x varies from 0 to a and y will vary from 0 to a minus x. So now throughout it will be a minus x. So whatever the value of a minus x, let us take a few values in between. So let us say we have 0 comma 0 three boundaries, 0, comma 0, a comma 0, and 0, comma a. Let us see how they look. Now 0, comma 0, u will be 0, b will be undefined. So it goes to infinity. Now um, u x plus y is a, and v will be 0, and this again will be a, this will be 1. So in the x uv plane, this triangle transforms in a very different manner. Now, and there are so many points in between. It is not just on the line. There are so many points in between this region. All that region has to be transformed. So the boundaries 0, comma 0 is u is 0, v is infinity. Okay. Then we have a comma 0. And we have a comma 1. And 0, comma infinity. This so this region, it's now whether it's a curve, it has to be a curve because it's going to infinity. This will be the region. So I, the integral will be integral now when y is equal to a minus x. Let us take some point. This is x, this is a minus x. Then u will always be a. U lies on this line, u will always a, and yeah, y is a minus x by x plus y will be a. So you get 1 minus x by a. Now this x in terms of u and v is a complicated expression. So you keep changing the points, you will get different points. So one boundary will always be along x equal to a, and see this line, this whole line will give one particular boundary. So now when we transform, we have v of x comma y into Jacobian du dv, limits on u and v. So the limits on u will be 0 to a, from v will be 0 to infinity. So 0 to a and 0 to infinity. V of x, what is x? U 1 minus v times uv into u du dv. This is the transformed integral. The last one, transform to polar coordinates. Now the integral are being extended over all positive values x and y subject to x square plus y square less than 1. So then what is this? This is a circle. So so the region of integration is this. Now when we convert this to r theta, uh, so limits on r will be from r theta is like any line you take. R will vary from 0 to this capital R is the radius unit circle. So this is 1 and this is theta. So now let us transform. X is equal to r cos theta. Y is equal to r sin theta. And Jacobian, we know the Jacobian, we calculated the Jacobian as r. So dx dy is r d theta dr. Now what is the limits? Now in this region, theta varies from 0 to pi by 2. This is easy, from 0 to pi by 2. And r, all the points within this. So r will, the distance from the origin will change from 0 to 1. R varies from 0 to 1. Okay. Now, what is x square plus y square? Is r cos theta the whole square plus r sin theta the whole square, which is r square. So we get I transformed integral is integral 1 minus of x plus x square plus y square. 1 minus of x square plus y square. So 1 minus r square by 1 plus r square under root 1 minus r square over 1 plus r square r d theta dr. So theta varies from 0 to pi by 2 and r varies from 0 to 1. So now now integrating with respect to theta, treating r constant. So we'll get integral 0 to 1 pi by 2 times under root 1 minus r square by 1 plus r square r dr. Okay. How to integrate this? Substitute. Now I have to eliminate this under root. And I have this r dr. So r square, if I put t, that also we can do that. I can put r square as t and r dr will be dt. Let us try that. Put so I will be integral. Now when r is 0, t is 0. When r is 1, t is 1. So limits of integration doesn't change. You have 1 minus t by 1 plus t dt. We rationalize the numerator. So 1 minus, so multiply and divide by under root of 1 minus t. So we'll get in the denominator under root of 1 plus t into under root 1 minus t is 1 minus t square dt. So this is equal to pi by 2 into integral, sorry, integral 1 minus t square plus integral 0 to 1 minus t by under root of 1 minus t square dt. The first one is sine inverse t.
No.
From
Sir,
0 to 1. Yes,
dt is equal to what here?
thank you. Thank you, man. So RDR will be half dt. So multiply by half, 1 by 2. So this is 1 by 4. Okay, thank you. Now here, I will further multiply and divide this by 2. So I get derivative by root of the function f dash x by under root of f of x. If f of x is 1 minus t square, then the derivative will be minus 2t. So pi by 4 times this will be sine inverse 1 minus sine inverse 0. This will be plus half into integral of f dash x by root f of x dx is 2 root f of x plus c. So antiderivative is this. So antiderivative for this function is under root of 1 minus t square. Put from 0 to 1. So here it is pi by 4 times pi by 2 minus 0 plus half of, substitute t as 1, you get 0 minus 1. It is 2 root t. So 2 and 2 cancels. 2 root of 1 minus t square. So 2 and 2 cancels. So we have the integral value is pi by 4 times pi by 2 minus 1. After transforming, calculating the integral. Okay. All right. So I'll just share with you the question bank. Just a second. So look at functions of several variables, applications of integrals. What kind of questions come? This is 10 years, 10 years of questions and gate just on application of integrals. There were questions. There are recent ones which I'll give you in tests in the last 5 years. This is prior to that. This is, see, find the length of the curve. This is function of a single variable. Again, of course, this is for in civil engineering. One of the problems of, cable held by a, parabolic cable, finding the total length of the cable. Again, it is a rectification problem. Um, it is a simple math problem only, rectification problem. Then area under curves. All right. Area under curves, very simple equations. A line and a parabola. Line, parabola and lines, two lines, area bounded by. Then curve given by this equation is symmetric about x-axis, y-axis. So curve tracing concepts. And this curved is volume of Descartes, which we have done. X square plus y square equal to 3xy. The number of points of inflection on this curve, it is just a derivative part, it is not integral. Then area enclosed between, again, parabola and line, area enclosed between the two parabolas. This problem we have done both by, double integral as well as the single integral. Then area enclosed between straight line and parabola. So there are simple questions here. Solids of revolution. See. Volume generated by revolving the area bounded by the parabola and the line x equal to 2 about the y-axis. All right. Then the parabolic arc is revolved around the x-axis. Volume of the solid of revolution. Then multiple integrals, evaluation of double integral, reversing the order of integration. Okay, this is not a change of variable, it is reversing the order of integration. Next, this is a question on a double integral, simple. Then volume of object expressed in spherical coordinates. Now, r square sine phi dr d phi d theta. This is the Jacobian, if we know, of the spherical coordinates. Yesterday we did. This is nothing but dx dy dz. Now we can calculate, 0 to 2 pi. Now this is from 0 to pi by 3. 0 to 1 is r. Maybe azimuthal angle is from 0 to pi by 3. And this is 0 to 2 pi. Of course, we can just do this as a triple integral. You don't have to do one after another. Integrate first partially with respect to r, then with respect to phi, and then with respect to theta. We can calculate this. Then change the order of the integration again. So change of order. Next, change of variables in double integral. X is uv and y is u upon v, v upon u. Okay. Then what is phi of something is incomplete here. I think this is a Jacobian problem. This should be j of u comma v. I'll cross check this. So this is about change of variables. Then this is double integration. Simple problem. Double integration. Consider the shaded triangular region. Figure is missing here. I'll give this question again, but if figure is given, find out what is the double integral. Value of the integration of a function along straight line segment. This from 0, 0 to 1, 2. So in the xy plane. So this line integral we will be doing using vectors. This need not be a double integration problem. It is a linear problem along the line. In vector line integrals we will be doing. Now, then this one is volume of area bounded by area under f of x comma y. We don't have to calculate. It is just asked that x and y both lie between 0 and 1. And x is greater than y square and y is greater than x square. So this is the region. Now, how do you find this out? So these are the problems. Now, I will give this as a test to you. You first work out, or maybe in the next class, I will give this in class time, or I'll give a quiz. You work it out. You work these questions out and get back to me. I will soon give these questions to you. So you can see a number of questions come. And from all areas, whatever area we have covered, some question or the other is touched. All right. So all right, next we move on to the next topic. So we begin with this topic of vector algebra. As a review, before we do vector calculus, actually, topic now we are going to discuss is vector calculus. We are beginning with the review of vector algebra. Algebra of vectors. First, definition, and then types of vectors. We'll just go through it very quickly. So any quantity which has both magnitude and direction is a vector. A scalar doesn't have a sense of direction, like temperature, mass. It doesn't have direction. Temperature, mass, speed, distance. These are terms which does not have direction. However, terms like displacement, it has a direction. From one location, point A, an object moves to point B. So from A to B, it has moved. So it has both magnitude, the length AB, and the direction from A to B. Okay. Now, so displacement, velocity, acceleration, momentum is mass times velocity. So it will be weight, mass times acceleration due to gravity, force. These are all vector quantities. So vector is a quantity which has both magnitude and direction, and we represent a vector by PQ. P to Q, from P to Q, we give an arrow. So the vector is represented by PQ with a top arrow, or we simply write, let's say this is a vector A. We write it this way. So P is called as the initial point. P is the initial point and Q is the terminal point. So this PQ we define in terms of length, and so this variable A usually denotes the length AB, and on top of that, if we draw an arrow, it represents a vector. So the modulus or module or magnitude of a vector is a positive number, which is the measure of the length and is denoted by modulus of A. So length A denoted as modulus of A. And sometimes it is, in many textbooks, it is written as bold letter A for modulus. Now, what are the types of vectors? Most of it we know. So zero or null vector is a vector whose initial and terminal points are coincident. So they are called as zero vector. Now its modulus is zero, very important. Modulus of zero vector is zero, and the direction is indeterminate. You cannot ascertain what is the direction of the zero vector. It can be in any direction because initial and terminal points are coincident. Now, from which direction they are coincident, we can't say that. Now, unit vector is a vector whose modulus is unity. We know this. The unit vector is okay. The unit vector, the direction of a vector A bar is denoted as okay, unit vector in the direction. Unit vector in the direction of a vector A bar is denoted by A cap. So unit vectors are denoted by a cap, a hat. Then like vectors and unlike vectors. Vectors are said to be like when they have the same sense of direction, and unlike when they have opposite sense of direction. So vectors need not be equal. Like vectors need not be equal. So this is vector A and this is vector B. They are like vectors as long as they are parallel. They have the same sense of direction. And they are unlike vectors if the direction is opposite. So A and C are unlike vectors, B and C are unlike vectors, but A and B are like vectors. Okay. For us, this property is most vital. Equality of vectors. Two vectors A and B are said to be equal and written as A equal to B if they have same length, same or parallel support, very good, and the same sense of direction. Three points. Equal vector does not mean nowhere it is mentioned that it should be of the same starting point and the same terminal point, the same initial point and the same terminal point. It is not necessary. It is not at all necessary. So equality of vectors, what we do is like two vectors are said to be equal if they may be lying on the same line of action. I'll erase this. Let's say this is a line of action. This is another parallel line. This is vector A. This is vector B of the same length as that of A. Vector A, vector B. So now A is equal to B. A bar is equal to B bar. Now B bar can be acting on the same line of support. This is called as the line of support. Line of support. Now it can be acting on the same line of support or a parallel line of support. Same line of support or parallel line of support. So two vectors, so A and B, they need not be on the same line. They need not start from the same initial point and same terminal point. As long as they are parallel and equal in magnitude, they are considered as equal vectors. This is a very fundamental understanding of vectors. It need not have the same initial and same terminal point. Okay. Next, collinear and parallel vectors. So vectors having the same or parallel supports are called as collinear vectors. Now, because of the previous condition, you see, when you say collinear vector, it need not be. So now A and B, they will be called as collinear vector because I can shift B to any initial point and terminal point. As long as the magnitude and direction is constant, I will get the same result. Got it? As long as the magnitude and direction is the same, no matter where I keep, it will be the same. So I can keep the vector B in the same line of support or a parallel line of support. They are still called collinear vectors. Very important. Coplanar vectors. A system of vectors is said to be coplanar if their supports are parallel to the same plane. Note that two vectors are always coplanar. Very interesting definition again. Vector algebra. Now, this is a plane. This is vector A. Now, this is vector B parallel to the same plane. This is parallel to the same plane. So that vector B, as long as I can maintain the magnitude and direction, I will coincide the vector B's initial point with the initial point of vector A. This is vector B. Now they both lie in the same plane, correct? So vectors A and B are coplanar. If the lines of support lie in the same plane or are parallel to the same plane, that is the idea. And any two vectors, no matter which is the direction, what is the direction, doesn't matter. We can, put them and with the same initial point, and we can pass a plane which contains both of them. So any two vectors are always coplanar. Very important result, or very important understanding. So a system of vectors is said to be coplanar if the supports are parallel to the same plane. Note that two vectors are always coplanar. Next, co-initial vectors. Vectors having the same initial point as are co-initial vectors. We don't generally deal with vectors in this sense unless there is a problem of force acting at a point. We have to consider the way which point is the force acting. Then co-initial and co-terminal vectors uh, are important. So coterminous vectors are vectors having the same terminal point. Next, negative of a vector. A vector which has the same magnitude as vector A but has opposite direction is called negative of A and is denoted by minus of A bar. Reciprocal of a vector. Vector having the same direction as that of A, but the magnitude is equal to the reciprocal of the given vector and is known as the reciprocal of A bar. This is a definition, but it is not so much used. Localized and free vectors. A vector which is drawn parallel to a given vector through a specified point in space is called a localized vector. So if we specify through a specified point, we are specifying a point through which the vector should either start or end, or it should pass through, then it is a localized vector. Now, if the value of a vector depends only on its length and direction and is independent of its position in space, it is called as a free vector. So in this chapter, we will be dealing with free vectors unless otherwise stated. A free vector can be taken anywhere in space, choosing an arbitrary initial point. So here we were moving vector B from this point to this point, this line of support to this line of support. So these are free vectors. Now in this plane, we shifted this vector B from this position onto this plane. These two are the same vector B. So this is what is a free vector. It is not restricted to an initial point and the terminal point. So that's the way we deal with vectors as free vectors, unless in some load bearing problems, the location of vector where it is acting is very, very important. So we cannot change, like engineering mechanics problems, or in strength of materials problems, you cannot change the location of the force. So it is other than that, vectors in general are free vectors. Okay, like moment is a free vector. Moment of a force is a free vector. Next, the most important and the vital concept we will use again and again is the concept of position vector. Now, position vector is with respect to a fixed origin. So if O be a fixed origin, and P be any point, then the vector starting with origin as the initial point and P as the terminal point is called as the position vector of a point with respect to the origin. Now, this position vector need not be restricted to a two-dimensional uh, space. It can be a 3D. So we can have X, Y, and Z direction like this. This is the origin O. And let's say P is some point in space. It is not an XY plane. Now it has coordinates X, comma Y, comma Z. So this vector OP bar is called as the position vector. This plays a very key role in all vector calculus problems. So this OP bar is the position vector of P. So we'll discuss further. Next, addition of vectors. Very, very important. Very important. Okay. Properties. Two simple properties. First, let's study addition carefully. Um, so addition of vectors, it follows the triangle law of addition or parallelogram law of addition. So triangular law, like I have to add two vectors A and B. All right. So triangular law says like I take the vector A, take the uh, initial point and terminal point of vector A, coincide the terminal point of vector A with the initial point of vector B. So then I'll complete the triangle by joining the initial point of vector A by the terminal point of vector B. This will be A plus B. Okay, this is A plus B. So triangular law of addition, that if two sides of a triangle, uh, along the two sides of a triangle, if a vector is placed, the third side will represent the sum of the sum of the two vectors, as long as, remember, they are joined in a series kind of a thing. That means the terminal point of the first vector is coinciding with the initial point of the second vector. Then the addition will be from initial point of the first to the terminal point of the second. This is how the addition is defined. Now, the same holds true that if we draw a parallelogram, okay, we draw a parallelogram with the vector A and vector B. We place vector A and vector B along the two adjacent sides of a parallelogram. Then the diagonal, so this is vector A, this is vector B. The diagonal starting from the same. So we have made this as co-initial vectors. That means A and B have been placed starting from the same point along the two sides of a parallelogram. We complete the parallelogram. Then okay, it's not starting from the same point. I'll start like this. Then the diagonal represents A plus B. The diagonal represents A plus B. And the same as the triangular law, B can be shifted here. So A plus B, according to triangular law or parallelogram law, is this way. So according to parallelogram law, it is the diagonal. And according to the triangular law, it is the third side of the triangle. So this is the parallel addition of two vectors always. Now magnitude of A plus B is not equal to the sum of the magnitudes because of the triangular inequality. The sum of two sides of a triangle is always greater than the third side. So A plus B is the third side. So when you take the modulus, it gives the length. So length of the third side, modulus of A plus B, will always be less than the modulus of the other two vectors, individual vectors. Sum of the two sides is greater than the third side. That's why we get this. And also the difference of the two sides will be lesser than the third side. So third side will be greater than the difference of the two sides. This is a basic geometric property. Now, equality will hold if they are collinear. If A and B are in the same direction or in the opposite direction, then the equalities will hold. And properties of addition, the vector addition is commutative. A plus B is same as B plus A. So A plus B gives the same third side and B plus A gives the same third side. So vector addition is commutative, vector addition is associative. And polygon law of summation of vectors. Polygon law. Stop. Just a second. Now in polygon law, suppose we need to find sum of a number of vectors a, b, c, d, e. Let's say 5 vectors a, b, c, d, e. So let's say this is a. Now we will just draw all in a sequence. The terminal of a will coincide with the initial point of b. Then the terminal of b coincides with the initial point of c. Then the terminal of c coincides with the initial point of d. And terminal of D coincides with the initial point of E. So if we do like this, so in a sequence, we have plotted the vectors like this. Then the initial point of A and the terminal point of E, if you join vector, this will be A bar plus B bar plus C bar plus D bar plus E bar. Okay. So this will be the last, if we put, the vectors along the sides of a polygon, the last connecting side will be the value of the sum of all the vectors. So we can keep doing this by vector sum of two vectors and then show that this is true. This will be a plus b. This will be a plus b plus c. This will be a plus b plus c plus d. And then this will be a plus b plus c plus d plus e. So we can closing the polygon. Now suppose while we draw the polygon, the terminal side of E, terminal point of E coincides with the initial point of A. That means the sum of all the vectors is 0. It's a null vector. So if the terminal point of the last vector coincides with the origin of the first vector, then the sum of the vectors is 0. All the vectors. So this is the polygon law of addition. Now, based on addition, this is something very basic and fundamental. For all position vectors, we use this very, very often. Now, expression of vectors of a vector in terms of the position vectors of its endpoints. Position vectors of its endpoints. So now let us take a 2D case. This is origin. Now let us say we have 2 points A and B. Okay. Now through this we can draw the position vector of OA. This is point A. This is point B. And this is position vector of B. So position vector is line joining the vector joining the origin to the point. This is a position. Now I want the vector AB. I want this vector, vector AB. Now vector AB, so this is A bar, B bar. Sometimes we write the vector like this, like in coordinates, x comma y, we write the point, we write A as A bar. That means it has, this is the position vector of A. B of B bar means this is the position vector of B. Now, what will be AB? Now, based on the triangular law of addition, OA bar plus AB bar will give me OB bar. Triangular law of addition, OA bar plus AB bar gives me OB bar. This is the triangular law of addition. So the position vector is A bar plus AB bar minus B bar. So AB bar is B bar minus A bar. So position vector, it's the position vector of terminal point minus the position vector of initial point. Position vector of A. So a vector AB bar can be written in terms of the position vector of 2 points. So this makes it very easy. Now, coordinate geometry and vector algebra, 3D coordinate geometry and 3D vector algebra, they go hand in hand because you can convert problems from of vectors to coordinate geometry and coordinate geometry to vectors. So that's how it works. So you get position vector of B minus position vector of A. That is AB bar. And BA bar will be position vector of A minus position vector of B. Okay. Next is linear combination of vectors. Linear combination and then linearly dependent and independent set of vectors. This is part of linear algebra also of vector spaces. This is a very simple concept, but it's an important concept. All right, let us look at this. If a vector R is expressible as x times A bar plus y times B bar plus z times C bar, let us say, and this need not be there. So this need not be there. Okay. So R bar is x times A bar plus y times B bar plus z times C bar. Where x, y, and z are scalar. So we are able to write a vector R as a combination of three vectors multiplied by scalars. So scalar multiples. So then we say it is a linear combination. Why is it linear combination? We are not squaring it. We are multiplying with scalar multiples of the vectors. We are not multiplying with the vector with a vector. So these are called as linear combination. Then linearly dependent and independent set of vectors. So a system of vectors A1 to AN is said to be linearly dependent if there if there exists a system of scalars lambda 1, lambda 2, lambda 3 up to lambda n, not all zero, such that the linear combination of them is zero, such that the linear combination of these vectors is zero. That means they are called dependent. Dependent means one of them can be expressed in terms of the others. So let us say lambda 1 is not zero. If lambda 1 is not zero, I can write a1 as minus lambda 2 by lambda 1 a2 minus lambda 3 by lambda 1 a3 so on minus lambda n by lambda 1 an, because this is holding true and not all are zero. So let's say lambda 1 is not zero, I can write a1 in terms of the other vectors. Then these are called as dependent vectors. But if a system of vectors which is not linearly dependent is called linearly independent. Now, what is a linearly independent vector? A set of vectors is said to be linearly independent if every relation of this type, that means a linear combination of a1, a2, an is zero, implies that all their scalar multiples are zero, which means you cannot combine them. You just cannot uh, combine them to make it zero. For example, all right, example of simplest vectors, we know I cap and j cap. I cap is a vector along the x-axis. J cap is a unit vector along the y-axis. Is there a way, now these are perpendicular, is there a way that I multiply I cap by x and j cap by y such that their sum becomes zero? The only possibility is x equal to 0, y equal to 0. Because you cannot combine these two to make them zeros. So these are independent. I cannot write I in terms of j. I cannot write I cap is equal to some x times k cap. This is not possible. X times, sorry, j cap. This is not possible because they have a different sense of direction. We cannot combine the two. However, another vector, let's say along I, this is like 3i. Yes, this vector, let's say this is vector a bar is I cap, vector b bar is 3i cap. Now I can write b bar as 3 times a bar. So a and b are dependent vectors. One vector can be written in terms of the other vector. But we cannot write, you know, j cap in terms of I cap or I cap in terms of j cap. So they are linearly independent vectors. So if a linear combination of I cap and j cap is a null vector, it means that both the scalars x and y are zeros. That's the only possibility. That's the idea. Now, if I include one more vector in xy plane like this, okay, xy plane, maybe at a 45-degree angle, and let's say the length is 2 root 2, then I can write this vector. Let's say this is b bar j. A bar is I. Now let's say this is C bar. Now the C bar I can write here only. I'll write C bar I can write as 2I plus 2J. I can write this. We know this, that we can write this. So C can be written as a linear combination of I cap and J cap. So this vector C and I cap and J cap are dependent vectors. They are not independent vectors. One of them can be written in terms of the others. So, um, so C bar is equal to 2A cap with A bar plus 2B bar. So I can write A bar in terms of B and C. I can write B in terms of A and C. So on. So that's the concept of linearly dependent and linearly independent vectors. So now this note is very, very important for this. A vector along a line is independent. Yes, a single vector along a line is independent. But two collinear vectors are always linearly dependent. So because one of the vector can be written as the linear combination of the other. So A bar and B bar, if they are collinear, then A bar equal to lambda times B bar. Next, now any two vectors are coplanar. The next point, any two vectors are coplanar. Let's say two non-collinear vectors. Two non-collinear vectors. That means they're not parallel. In a plane are linearly independent. As long as there are two parallel vectors, just two non-parallel vectors, A and B in a plane, it is impossible to write one in terms of the another. Okay. So two vectors, two non-collinear vectors in a plane are linearly independent. But if a third vector is included in the same plane, then it becomes a linearly dependent system because the third vector can be written as x times A bar plus y times B bar. This is based on the addition of vectors. Then similarly, three non-coplanar vectors in space are linearly independent, I, J, K. So the condition is they should be non-coplanar. They are linearly independent. But if you include a fourth vector in space, then it becomes a linearly dependent system. So I cap, J cap, K cap are linearly independent systems. These three form a linearly independent system. I, J, K cannot be written in terms of each other. But a fourth vector can be written in terms of I cap, J cap, K cap. So this is the concept of linear dependence and linear independence. Okay, test for very quickly. We'll go through this. It's not so critical. See, uh, so far what I described is very, very important. And the basic fundamental understanding of vectors. Now test for collinearity and coplanarity. Now the first method, if three points, if 3 points are collinear, so there are 3 points along a line. This has the position vector A bar. This has the position vector B bar. This has the position vector C bar. So 3 points are collinear. Then what happens is A bar AB bar or and AC bar, or AB bar and BC bar are linearly dependent, because they will be parallel vectors, right? AB bar and say BC bar. So I can write, because they are parallel vectors, I can write BC bar as some scalar multiple times AB bar. So if we can show this, then they are collinear. Okay. Now second method to show is that to prove the collinearity of 3 points, A, B, C are position vectors. Now 3 points with position vectors A, B, C are collinear if and only if there exists scalars x, y, z not all zero, such that this condition holds. Two of them should hold. The linear combination of A bar, B bar, C bar should be zero, such that the sum of the coefficients of this linear combination will also be zero. Okay, this is test for collinearity. Then test for, you know, test for three vectors to be coplanar. If three vectors A, B, C are coplanar, then one of them can be expressed as the linear combination of the other two. So A can be expressed as a linear combination of B and C. So that is coplanarity. And method to prove that 4 points, these are not vectors, 4 points are coplanar. First method is to, again the same. If 4 points are there in a plane, A bar, B bar, C bar, and D bar, then what happens? AB bar, AC bar, let this point C be here, AD bar. Now these will be coplanar. So we can write, let's say AC bar as a linear combination of AB bar and AD bar. If we can show this, then these are coplanar. Other way to show is that this X, Y, Z, U, D. So basically we can show that these are coplanar. We can find non-zero. I will write this as X times AC bar plus Y times AC, X times AB bar, Y times AC bar, and Z times AD bar is equal to 0 if there is a linear combination. So that means X times B cap minus A cap position vectors plus Y times C cap minus A cap plus Z times D cap minus A cap is 0. That means now coefficients of A you collect minus x minus y minus z. So minus x minus y minus z times a bar plus x times b bar plus y times c bar plus z times d bar is equal to 0. So what we are saying is the sum of the coefficients of a bar, b bar, c bar and d bar, the sum will be 0. So that is this point. We can find x, y, z, u for a bar, b bar, c bar, d bar such that the combination is 0 and their relative, their respective sum of the coefficients will be 0. Just in addition, we have not gone to multiplication. So in addition, further results. So ratio formula, if a point, um, there is a line joining 2 points, A and B. A has position vector A bar, B has position vector B bar. Then a point P which divides AB in the ratio M is to N is, it divides AB in the ratio M is to N. Actually, this should be reverse. It should not be M times A bar. It should be M times B bar plus N times A bar by M plus N. It is M times B bar plus N times A bar upon M plus N. And the midpoint will be A bar plus B bar by 2. Centroid of a triangle formed by 3 points will be A plus B plus C by 3. So these are some standard, these are just reviewing this. This is something very important. The direction cosines, this part will be very, very useful for us in vector calculus. So any vector in space can be written in terms of orthonormal set system of unit vectors. What are the orthonormal system of unit vectors? I, j, k. I cap, j cap, k cap. So these are unit vectors along x-axis, positive x-axis, positive y-axis, and positive z-axis. So any vector OP can be written as a linear combination of I, j, k. So a point P, as we described earlier, so this is I cap, j cap, k cap. Now P is a point in space. Let's say its coordinates is x, comma, y, comma, z. So we can show that I can't draw a 3D shape with these figures, but we can show very clearly All right, what we are drawing is a, cuboid or rectangular parallelepiped, all right, with, three sides. This is, let's say, um, yeah, this is the origin. This is the x-axis. This is the y-axis direction. And this is the z-axis direction. And this is the point P. P has coordinates x, comma y, comma z. So now, if P has the coordinates x, comma y, comma z geometrically, now this is x distance, right? This is, uh, let's say, OA, OB, and OC. OA will be x times I cap. Unit vector along x direction is I cap. Multiply with x, you will get the length, right? OB is y times j cap. And OC is z times k cap. Now, OA plus OB plus OC will give the diagonal of the parallelepiped here. Oh. So this is the vector OP. OP will be OA bar plus OB bar plus OC bar. So we can write the vector OP bar in terms of the coordinates I cap, xi cap plus yj cap plus zk cap. So very easy now to convert a problem of coordinate geometry. So if the point has, in the 3D Cartesian system, coordinates as x, comma y, comma z, then the position vector of that point with respect to the origin OP bar is x I cap plus yj cap plus zk cap. So now this OP, let us say it makes angles with this OP and OA. So OP makes an angle of alpha with the x-axis, and it makes an angle of beta with the y-axis, and it makes an angle of gamma with respect to the z-axis. So cos of these angles are called as the directional cosines. Cos alpha, cos beta, cos gamma are called as the directional cosines. They are represented by L, M, and N. Now, L, M, and N are such that the sum square of the sums, L square plus M square plus N square, will be 1. Cos square alpha plus cos square beta plus cos square gamma will be 1. The directional cosines, the cos of this, see, length OP, we know, is under root of x square plus y square plus z square. The distance formula, distance between O and P, is under root of x square plus y square plus z square. So this is nothing but the magnitude of this vector OP bar. Now cos alpha is the length OA by OP, which is x upon root of x square plus y square plus z square. The length of the cos beta is OB by OP, and cos gamma will be OC by OP, z upon root of x square plus y square plus z square. Okay. So these are direction cosines. So x square plus y square plus z square we can write as R. So we get L, M, and N are the direction cosines, and the unit vector along OP, R cap or OP cap, is OP bar by modulus of OP unit vector will be L times I plus M times J plus N times K. So this is what is this. So these are important results. So we just covered addition of vectors. We still have multiplication of vectors. So what I would have taken usually 4 or 5 days for a beginner's class, for you in 1 hour or 1 hour 15 minutes I've covered. But these are very, very vital concepts. They are uh, none of these concepts what I told can be ignored. There's a very compact summary that I have given and detailed. None of the points are missed. So this will be very, very helpful to you. The next class that we'll have multiplication of vectors. That's it. And some geometrical application of vectors, vector equation of a plane. Very simple. And then we move on to vector calculus. And in vector calculus, some of these things we will be very often using, some of them will not be using. All right. Do you have any questions?